So we're learning about a unique aspect in elastic collision. In elastic collision, there's no loss of energy, right? So the energy before the collision and after the collision remains within the system and not lost to any heat or deformation or sound and things like that. So there is a unique aspect of elastic collision, and that is the relative velocity of approaching. Velocity of approach before collision is equal to the relative velocity of the separation after the collision. So I'll explain this post the derivation. So let's look at the three case. So before collision, you have two objects. Of course, the one which is behind has more velocity. So during the collision, we get to see this, and after the collision, we'll get to see this, right? Actually, anyways, the lens can be anyhow. Now, 1 minute, not happy with. Okay. So now let's start the derivation by considering what we just learned in the previous video. As linear momentum is conserved in a collision. So it doesn't matter which collision, even though this is elastic. So we have the initial momentum being equated to the final momentum, right? Now a bit of rearrangement and we end up with m1 u1 minus v1. Okay, if I send this across, and then m2 v2 minus u2. So this we'll be using a bit later. So I can call this as 1 or something. Okay, then we have as kinetic energy is conserved in elastic collision. So this is specific to elastic collision, right? So basically we have the kinetic energy before the collision. They have to be equal to energy after the collision. That's the whole idea of inelastic collision. Now again, we'll rearrange and get all the m1 at one side. And by the way, we can divide 2 off. Cancel 2 off, that is. m1 u1 square minus v1 square is equal to m2 v2 square minus u2 square. Okay, so we have m1. So we have a square minus b square form, right? Let me do that later. Okay, where is that I'm going with this? I'll call this as 2. So if I take up 2 divided by 1, so we have m1 getting cancelled, and you end up with m1 u1 square minus v1 square divided by u1 v1. You can actually skip this step. m1 times m1 is equal to m2 divided by v2 square minus u2 square m2 v2 minus u2. So you can skip this step, and of course this is to be written to understand, but if you don't have time, you can directly write this. So this is in the form of, numerator is in the form of a square minus b square. So we have u1 plus v1 divided by u1 minus v1 is equal to v2 plus u2. Okay, I'm directly writing this. I don't have space because this and this will get cancelled. Is it not? So bit of rearrangement. Again, all the u's I'm getting at one place and all the v's I'm shifting to other. So what is that we are looking at? This is nothing but relative velocity of object 1 with respect to object 2 will be same as relative velocity of object 2 with respect to object 1 after collision. This is before collision, remember. So basically this is telling before collision relative velocity of 1 with respect to 2, right? This talks about after collision relative velocity of 2 with respect to 1, that they are equal. Okay. So I have an example for you guys that will make it a bit clear. Say we have object A, object B, and the mass and the velocity. So initially this is at, okay, the mass will not change. All of this is in kg. And this is in meter per second. So this is chasing this, okay? This is a before scenario. Now let's look at when you do the calculation and everything, we'll end up with so this is going to be 4 and this is 9. Okay. So what we're looking at is u2 minus, sorry, u1 minus u2 will be equal to, what is u1? u1 is 10 minus 5 is equal to 5, right? And v2 minus v1, v2 is 9 minus 4. Okay, so this is v1 and this is, in our case, we took it as a and b actually. So let me do that itself. vb minus va, vb is 9 minus 4, this is 5. And here is ua minus up, 5. Can you see that numerically they will be equal? Of course, I didn't show you guys the calculation, but you guys can do the calculation, you know. So you guys can figure out the after collision what is the velocity. So you can use your momentum and stuff like that. So many ways of calculating, but you will be able to calculate these values. So basically, in terms of words, so let me put it this way actually. Let me show you guys this. So the rate at which the first object is coming in, this is the elastic collision, close to elastic collision that I have, a video close to elastic collision that I have. So the relative velocity of the leftmost ball bearing compared to the one which is coming. So we can have a look at it. So here initially it is 0 and this is some value, say 5. Now this became 0, the right one became 0 and the left one will move at that rate. Okay, so if I happen to do the math in this manner, I'll get 5 and 5. Okay, so I'll show it again. If the incoming object's velocity is 5, and the outgoing object's velocity will be 5 because they are of the same mass and everything, the calculation will turn out to be the same. Here there is change in velocity, but in that example, the velocity will remain the same. Okay, point is the relative velocity with this combination will be the same. Okay, so with that example, wherein you had bunch of other objects and this, So we have this to be 5 meter per second, and this is 0. And after the collision, this became 0. So this came and hit, and this started moving. So this is 0 meter per second, and now this became 0 meter per second, and this is 5 meter per second. So if I take u1, this is u1 minus u2, this is v1 and v2. So u1 minus u2 is 5, while v2 minus v1 is 5. Does it make sense? u1 minus u2 is 5, v2 minus v1 is 5. Right? So the relative velocity of 1 with respect to 2 is same as relative velocity of 2 with respect to 1. Okay, so this is to do only with your linear momentum. Sorry, this is the derivation, right? Sorry, what am I telling? This is to do only with your elastic collision in one dimension.